Hello all. So today we are going to be working on utilizing the chain rule to take derivatives. I will be going through several examples with you, and I will point out that the only derivative rules I'm going to be using in this video are our basic rules, so that would be my power rule. I'm going to use our trig rules as well, along with the chain rules. So derivatives using the chain rule. And before we get started, I'd like to have some reminders. So first of all, I am going to write down our power rule, just to make sure you remember it. I am not going to take the time to write down all of our trig rules, so if you need a refresher on those, go take a look now and then come back to the video. So our power rule says I want to take the derivative with respect to x of some a times x to the n. So a is just a constant coefficient, n is also a constant, which is my exponent, and x is my variable. What we're going to do is kind of just ignore the constant coefficient. I just leave him alone, leave it there. I bring down and multiply my exponent n, and then decrease my exponent by 1. That's my power rule. And this brings us to my two little reminders that we're going to use a little bit today. We're thinking to ourselves, well, my goodness, the power rule is quite easy to use. And so if I could get everything in this form, a times x to the n, I'd like to try. And so to do that, we have a couple of rewriting tricks that we can use. One of these is if x is under a root. So say x is under a bth root, and maybe it has an exponent a. Then I can rewrite this as a fractional exponent. So keep your exponent in the top, the type of root in the denominator, x to the a over b. These are equivalent, but now this would allow me to use the power rule. Another situation where this occurs is if x is in the denominator of a fraction. I'm just going to put 1 in the numerator, but it could be another constant. And let's say I have an x to the a in the denominator. Now I notice that I can't use my power rule on this yet, but it is just x to some exponent, so I'm thinking maybe I could rewrite it so that I am able to use my power rule. And certainly enough, this is equivalent to just writing x with a negative a as the exponent. These, again, are equivalent. I'm just kind of being smart and rewriting it so that I can use my power rule. All right, that's it for my reminders, and now we're going to move along to using the chain rule. Now, I utilize the chain rule when I want to take the derivative of a function where it is a function with another function nested inside. So I'm going to write this as f of g of x. And to take the derivative, the chain rule says to take the derivative of f, leave g inside, then multiply, take the derivative of g. But I find it easier to think of it like this. It's a little bit more generic so that you can apply it to all kinds of examples, and it doesn't matter what the name of the function is or anything like that. I like to think of f as my outer function. So it's the outermost operation of this function. And then I like to think of whatever is nestled inside as the inner function. And now let me rewrite this rule using this outer and inner idea. So first it says f prime, and then keep g of x inside. So I'm going to find the derivative of my outer function, and I'm going to keep the inner function nestled inside. Meaning do not change the inner function. It stays exactly the same and it stays nestled inside the derivative of the outer function. Then I'm going to multiply. And then notice, then I attach times g prime of x. Now I'm going to take the derivative of the inner function. Okay, let's just dive right in with an example. I'm going to do quite a few examples to get you used to this. And I'm going to be lazy. I'm not going to say, oh, find the derivative, whatever. I'm just going to write the function down and we're going to find the derivative. So f of x here, the first example, is going to be 5x cubed plus sine x to the 10th power. Now, I chose this example because I think this is one of the most obvious uses of the chain rule. And I might be thinking maybe I could use my basic rules if I actually multiplied this all out, take it to the 10th power, but that would take quite a while, right? And so instead, we're going to utilize our chain rule. So I notice that this 10th power is like my outer function. And this 5x cubed plus sine x is nestled inside. It's my inner function. Okay. Now let's follow our rule. So now I want to take my derivative with respect to x. And look at what I have written up here. I'm going to take right here the derivative of the outer, keep the inner, times the derivative of the inner. So let's give it a try. I want to take the derivative of my outer function, which here is an exponent of 10. So I'm just going to utilize my power rule. I'm going to bring down the exponent of 10, and I'm going to decrease it by 1. Okay, so I've taken that derivative of that exponent of 10, and then it says to keep the inner function. So I'm going to keep the 5x cubed plus sine x. Okay, because it says to keep it inside, don't change it. Then you should be thinking to yourself, uh-oh, well, I need to take the derivative of what's inside eventually. And don't worry, it's not going to get left behind because the last thing we do then is take the derivative of the inner function. So then I need times, then I'm going to take the derivative of that inner portion. So let's do that next. So this part is already done. This was the derivative of the outer, keeping the inner inside. Now I need to take the derivative of 5x cubed plus sine x. So I'm going to bring down the 3 and multiply it. That'll give me 15 and decrease my exponent by 1. And then the derivative of sine is cosine. And there we have it. There's our derivative of f. By the way, you will get used to it, and you could probably skip over this portion where we wrote down, oh, and then we need the derivative of this. You could probably just skip to the end result at some point. So before we move on, and then I'm going to go a little bit more quickly through the examples, just make sure you don't do this very, very popular mistake. Oh, it's horrible. Don't do this. My students like to bring down the 10, decrease by 1, and then they make the mistake of putting the derivative of the inner inside. So they write the 15x squared plus cosine x inside. Oh, no, 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 no. Don't do that. Notice how it's written. I take the derivative of the outer and I keep the inner. Then you multiply by the derivative of the inner function. So don't fall prey to this mistake. Oh, heavens no. Okay? It's very bad, very bad. All right, let's keep going. Let's try another example. So I'm keeping these pretty simple for now, where they're just one usage of the chain rule. So now I have g of x. It's going to be equal to the cube root of 5x plus 1. All right, so notice I kind of have this outer function, which is the cube root, and then this inner function, which is the 5x plus 1. But we're not going to forget about our reminders where I said all the way up here, if I have a root, I really should write it as a fractional exponent. So I'm going to do that before I take the derivative. So I have 5x plus 1, and instead of the cube root, I'm going to write that as 1 over 3. I mean, these are equivalent. That is a cube root, but instead of writing it in that root form, I'm going to write it as a fractional exponent. And now this is still my outer function, and this guy is my inner function. Now let's go for it again. So let's take our derivative. First, I'm going to take the derivative of the outer function. That is the exponent of 1/3. So I'm going to bring down the 1/3 and multiply it, and decrease the exponent by 1. And now remember, I keep the inner function inside. I do not change it. No, no, no. Then you will multiply and take the derivative of the inner. Again, I'm just writing it like this to make sure we keep ourselves organized, but you could probably just skip ahead and just go ahead and take the derivative of 5x plus 1. And it depends how complicated it is if you want to put some extra steps in there. Oops. By the way, notice I'm not doing like any simplifying. That's really up to your instructor how much they want you to simplify, and so I'm not even going to pretend to know how much to simplify. All right, so the derivative of 5x is just 5, and then remember the derivative of 1, it's just a constant, so it's 0. Of course, we could at least simplify that to 5 plus 0 is just 5, but I'm just going to leave it alone. I'm just intending to do no simplifying. All right, let's continue on to another example. Keep making them a little bit trickier. So here I am going to have h of y, so we're taking the derivative with respect to y this time, e to the 4 secant y plus 1 over y squared. So that's all up in the exponent. I don't think I wrote it very well, but all of that is up in the exponent of e. And so a couple things. I notice I do still have like an outer and inner function where one is nested inside the other. And let's point that out first. So the 4 secant y plus 1 over y squared, that's nestled inside e. I think you would agree with that. So this is actually my inner portion. Even though now it's not under a root, it's not inside parentheses, but it is nestled inside this e function. So the e is actually the outer function. But I am going to rewrite this because I don't want to have 1 over y squared. Remember what I said way at the top? If I have 1 over x to the a, I'd like to rewrite that just so it has a negative exponent instead of being in the denominator. So let's do a little rewriting. I'll try to write this better too. So I have an e to the 4 secant of y plus y to the negative second. And now e is still your outer function. The stuff up in the exponent is your inner portion of the function. And let's take our derivative. Now we're going to be very careful here because remember that when I take the derivative of e to the x, what happens to it? It's just e to the x. It is its own derivative. So when I go to take the derivative of my outer function, this is a tricky one that professors use, okay? So when I go to take the derivative of my outer function, which is the e portion, nothing changes. And because I'm supposed to keep my inner function nestled inside, I truly just keep that original e 4 secant of y plus y to the negative second. Nothing changes at all for the first portion of the chain rule. Again, this is because the derivative of e to the x would be e to the x. And so when I go to take the derivative of the outer portion, it just stays the same. But then we do need to take the derivative of the inner portion, 4 secant of y plus y to the negative second. Okay, so we kept this portion, which technically we did do our derivative for e, it just didn't change anything. Then I'm going to go ahead and take my derivative of 4 secant y plus y to the negative second. So remember the constant coefficient, we just let it hang around. Now the derivative of secant is secant tangent. So I have a secant y tangent y. Plus, then I'm going to bring down the negative 2 and decrease it by 1. That's just the power rule. Now you're welcome to get rid of this plus because the plus negative 2 will just become a minus 2. Alrighty, and there's our derivative. And now let's do one more, just one more, where there's just one application of the chain rule. So I have my function m of x, and it is tangent of x squared plus the 5th root of x cubed. Again, notice I have an outer function, that's my tangent. And then an inner function, which is this x squared plus the 5th root of x cubed. And I'm hoping at this point you say, Haley, we need to rewrite that root. We're not going to forget that we should rewrite the root as a fractional exponent. So let's do that before we do anything else. So remember, I'm going to keep my exponent in the numerator because it's cubed, so the 3 in the top, and the type of root goes in the denominator. Now we're ready to use our chain rule. So we have that outer tangent and the inner x squared plus x to the 3/5. And let's go for it. I am hoping that at this point you're kind of catching on. Maybe you could try this one on your own and just make sure you get the same thing as me. So the first thing we're going to do is take the derivative of the outer function and we're going to keep the inner function nested inside. So the derivative of tangent is secant squared. So I take the derivative of the outer function and then keep whatever is inside nestled inside. Do not mess with it. No, no, no. Leave it alone. Then when you're doing the chain rule, you're thinking, well, eventually, though, I should be taking the derivative of the stuff inside, and I'm going to do that right now. Now I'll take the derivative of the inner portion. Again, you do not have to write out this step if you don't want to. You can just skip ahead to this step where I do all my derivatives. So I have my secant squared with the stuff nestled inside that I don't mess with. I leave it alone. So I just wanted to take the derivative of tangent and left everything else alone. Now I'm ready to take the derivative of the inner function. So I will bring down the 2, decrease my exponent by 1, plus bring down the 3/5, decrease my exponent by 1. By the way, if you do struggle with that, sometimes my students struggle with it. Perfectly understandable because fractions can be hard to deal with. If I want to bring this down and then subtract 1, instead of subtracting 1 from the fraction, like just writing down -1, instead, make sure you use the same denominator and just put it over itself. So I'm going to subtract 5 over 5 instead, and then I easily got -2 over 5. And hopefully now you'll never struggle with that again. And there's our derivative using the chain rule. Okay, I have 2 more examples left where we actually utilize the chain rule more than once. So here is my second to last example where I have f of theta, so this time we're taking the derivative with respect to theta, of cosine 6 theta, all to the 12th. And so as you're getting used to using chain rule, you're thinking to yourself, this looks like it actually uses chain rule more than once because I have this outer function of 12 to the 12th power, right? This is my outer function. Then my inner function would be the cosine of 6 theta, right? This is inner. But it kind of seems like I have a second inner function. So let's deal with that as we go, okay? So this one is going to be, I like to call it a double chain rule. Or if you'd like, a multiple chain rule or a multi-chain rule. So let's just start it out exactly as we know how. So I'm going to start by taking the derivative of my outer function. So that is an exponent of 12. So I'm going to use my power rule. I'll bring down the 12, and I'm going to decrease it by 1. Now remember, I always leave what's inside alone. I just leave it the way it is. So cosine 6 theta belongs on the inside. Then I'm going to take the derivative of whatever was on the inside. Now, when this happens, you think to yourself, well, this is actually also a chain rule, right? Where cosine is my outer function and 6 theta is my inner function. So, as I'm taking my derivative, I actually need to use the chain rule again. So I'm already done with that exponent of 12. Now I need to take the derivative of the outer function cosine, which remember the derivative of cosine is sine, and keep the inner function nestled inside. So it's a sine of 6 theta times the derivative of the inner portion, which is 6 theta. Finally, one more step and we will have our derivative. So I had the derivative of the exponent of 12, keep everything nested inside. Then I had the derivative of cosine. I'm sorry, this should be a negative sign. That's my bad. Keep the 6 theta nested inside. And then the derivative of 6 theta is just 6. And there is our derivative. So as you start getting these more complicated chain rules where you have to apply it multiple times, this is where I start to think of the chain rule as pulling back layers of my derivative. So let's look at where we started the derivative, which was up here, or the original function, to where we ended it. So notice I kind of peel it back one layer at a time. So first, I found the derivative of this outer portion, and I finished that, right? I brought down the 12, decreased the exponent by 1, left everything else inside. Then I moved into the cosine, made it into a negative sign, kept the 6 theta nested inside. Then I got to 6 theta, which the derivative was 6, and completed all of the layers of my derivative. So I kind of like knock everything out one at a time, starting from the outside and working inward. Okay. Let's do one. Again, I apologize about the cosine negative sign. See how easy it is to forget? So gotta be so careful with those. Gotta be so careful with our negatives when it comes to those trig derivatives. Okay, one last example Here, our function, let's go back to the classic f of x, and I'm going to have the square root of sine of cosecant of 5x to the sixth. Okay, hopefully at this point, this should be like screaming chain rule to you. And because I'm seeing so many functions, I see the square root, I see the sine, I see the cosecant, I know that it's going to be a multiple chain rule. Now, the first thing I'm still going to do is rewrite this as a fractional exponent. So it's going to be sine cosecant of 5x to the sixth, all to the 1/2 power. So I'm writing it as the 1/2 power instead of the root version. Yes? All right. Now you are welcome to give this a try and write out each individual step. And I think that that would be a great, great, great practice. But I want to show you how we're going to start from the outermost function and just start peeling off the layers for the derivative. And you can actually just do this in one fluent step. So stick with me here. I'm going to start with the outermost portion, which is this exponent of 1/2. I'm going to bring down the 1/2. And I'm going to decrease it by 1. That would be a negative 1/2. Everything that's inside that function stays the same. So I have a sine of cosecant of 5x to the sixth. Aha, so I've finished this portion. Oops, I wanted to use red, sorry. I finished that portion. I took the derivative of that 1/2 exponent. Let's keep moving inward. Now I need to take the derivative of sine, and the derivative of sine is cosine. And each time we take one of these layers, I leave everything inside the same. So I'm leaving in the cosecant 5x to the sixth. Okay, so I've peeled back another layer. I've taken the derivative of the sine portion. Okay, but notice I still kept the cosecant 5x to the sixth nested inside. Okay, let's keep moving inward. I'm going to move inward to cosecant. The derivative of cosecant is a negative cosecant cotangent. So I have a negative cosecant. Make sure to keep the 5x to the 6 nested inside. Okay, and now I've peeled back that layer of the derivative, and I'm on to my last piece, which is 5x to the 6th. This is my last derivative I need to take. I'm going to bring down the 6 and multiply it, so I get a 30x to the decrease your exponent by 1. And look how we were able to do that just in one shot, right? I actually I mean, there's multiple steps in it, but it's just one line of work. So that is a great way to think about the chain rule, is that you're just peeling back layers as you're taking the derivative. Okay, so I hope that this was at least somewhat helpful, and I'm going to stop us there.